Welcome to chemistry classes by Vijay Kumar Sethi. Class 11th chemistry. We were discussing unit 2 structure of atom, and in this video we will discuss about atomic models like Thomson atomic model and Rutherford atomic model. X-rays, radioactivity, atomic number, mass number, isotopes and isobars. First come to the Thomson model of atom. Thomson proposed that an atom consists of positively charged sphere and the electrons are embedded in it. Embedded means fixed firmly and deeply. You can see this diagram. This is a positive charge sphere and these are the electrons embedded in it. The negative and positive charges are equal in magnitude, so the atom as a whole is electrically neutral. What are the important features of this model? Thomson model explained that atoms are electrically neutral and mass of the atom is assumed to be uniformly distributed over the atom. But some drawbacks are also there. The results of experiments carried out by other scientists could not be explained by this model. And this model is also identified by different names. For example, this is also known as the plum pudding model or resin pudding model or watermelon. Okay, it can be compared with this. This is one sweet dish. Pudding means sweet dish, and I think watermelon, you are familiar with this. The red part of this watermelon is the positive sphere, and the seeds which are embedded in it are like electrons. Discovery of X-rays. Wilhelm Röntgen in 1895 showed that when electrons strike a material in the cathode ray tubes produces rays which can cause fluorescence in the fluorescent materials placed outside the cathode ray tubes. Means when electrons strike to the cathode ray tube, some new type of rays were produced. Clear? And since Röntgen did not know the nature of the radiation, he named them X-rays, and the name is still carried out. It was noticed that X-rays are produced effectively when electrons strike the dense metal anode called targets. These are not deflected by the electric and magnetic field and have a very high penetrating power through the matter, and that is the reason that these rays are used to study the interior of the objects. And again, you are familiar the use of X-rays. It can scan our body. Okay, and this is used to take the image of our body. These rays are of very short wavelength and possess electromagnetic character. Radioactivity. It was discovered by Henry Becquerel. Certain elements emit radiation on their own. These elements are known as radioactive elements, and this phenomena is known as radioactivity. This field was developed by Marie Curie, Pierre Curie, Rutherford, and Frederick Soddy. Radioactive elements may emit three kinds of rays: alpha, beta, and gamma rays. Rutherford found that alpha rays consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass. He concluded that alpha particles are helium nuclei. Yeah, alpha particles are helium nuclei, as when alpha particles combined with 2 electrons yielded helium gas. Beta rays are negatively charged particles similar to electrons. Gamma rays are high energy radiations like X-rays, and they are neutral in nature and do not consist of particles. If we compare the penetrating power of these alpha, beta and gamma, the penetrating power of alpha particle is least and beta particle 100 times that of alpha particles, and for gamma rays these are 1000 times of that alpha particles. Come to the Rutherford's alpha particle scattering experiment. Rutherford and his students Hans Geiger and Ernest Marsden bombarded very thin gold foil with the alpha particles. Okay? The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. You can see the setup of this experiment. This is the source of alpha particle, and these are passed through the hole of this lead plate. This is thin gold foil, and this is a circular fluorescent zinc sulfide screen. Okay. Question arises, why he selected gold? Actually, gold foil was selected because gold is the most malleable metal and he wants as thin a layer as possible. And as we already discussed, alpha particles these are doubly charged helium ions. This is simply we can say this is the helium nuclei. Now, what are the observations of Rutherford's alpha particle scattering experiment? Most of the alpha particles pass through the gold foil undeflected. A small fraction of the alpha particles was deflected by small angles. A very few alpha particles, about 1 in 20,000, bounced back, that is, were deflected by nearly 180-degree angle. You can see again this is one sheet of gold foil. Okay, these gold atoms are represented. You can see these are the straight lines, most are the straight lines. They are passing through the gold foil. Okay, and you can say this is deflected by small angle, and you can also see this one. This is also deflected. Okay, but you can say that is this one. Okay, this is going in this direction, again come back. This is bounced back. Okay, now what are the conclusions from this Rutherford's alpha particle scattering experiment? Most of the space in the atom is empty. Now, if we compare with the Thomson model, if Thomson model is correct, then all the alpha particles should bounce back, because according to Thomson, atom is positively charged sphere and alpha particle is also positively charged. That's why all the alpha particles should bounce back. But they are not bounced back, only few are bounced back. That's why we can say most of the space in the atom is empty. The positive charge is concentrated in a very small volume called nucleus. So we can say nucleus was discovered by Rutherford. The volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. If we compare the radius of the atom is about 10 raised to the power minus 10 meter, while that of nucleus is 10 raised to the power minus 15 meter. Now, on the basis of these conclusions, Rutherford put some points. These were known as Rutherford's nuclear model of atom. The positive charge and most of the mass of the atom is densely concentrated in extremely small region called nucleus. Electrons revolve around the nucleus in circular paths called orbits. Electrons and the nucleus are held together by electrostatic force of attraction. Okay, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. This is also known as planetary model of the atom. Now, what is atomic number? This is represented as a Z. The number of protons present in the nucleus is equal to atomic number. You can say atomic number is equal to number of protons in the nucleus of an atom, and as we know, atom is neutral. That's why number of protons are equal to number of electrons. That's why we can say Z is also equal to number of electrons in a neutral atom. Nucleons. Protons and neutrons present in the nucleus are collectively known as nucleons. Mass number represented as capital A. Sum of the total number of protons and neutrons present in the nucleus of an atom. Total number of protons and neutrons, and as we know, protons and neutrons are known as nucleons. That's why we can say number of nucleons are equal to mass number. Total number of nucleons is termed as mass number of the atom. We can say mass number is equal to number of protons plus number of neutrons. This formula is, or this relationship is again important. We can find out the number of neutrons if mass number and protons are given to us. Notation of an atom. How can we represent an atom? This X, this is the symbol of an atom of the element. This Z is the atomic number and A is the mass number. For example, nitrogen. Atomic number is 7 and if mass number is 14, this is represented like this. Okay. Now see some question. Calculate the number of protons, neutrons and electrons in this atom. Okay. Now if we observe this representation, then we can say Z is equal to 35, that is atomic number is 35 and A is a mass number is 80 and species is neutral because it is not carrying any charge. That's why this is neutral. Number of protons is equal to number of electrons. That's why we can say atomic number is equal to 35. And what are the number of neutrons? This is A minus Z. We discussed that mass number is equal to number of protons and number of proton is equal to atomic number. That's why Z plus N. From this we can say number of neutrons N is equal to A minus Z. It will equal to 45. Number of electrons, protons and neutrons in a species are equal to 18, 16 and 16 respectively. Assign the proper symbol to the species. Now as we know, atomic number is equal to number of protons and in this case number of protons is 16. That's why element is sulfur. And mass number is equal to number of protons and number of neutrons and both things are given 16 plus 16, that is mass number is 32. Now if you see the data, we can say atom is not neutral because number of electrons are 18 and number of protons are 16. Okay, that's why species is not neutral as the number of protons is not equal to electrons and it is anion because electrons are more and with charge equal to excess electrons and these excess electrons are 2. That's why it bears the 2 negative charge. That's why this is the symbol of the element. Isotopes. Atoms with same atomic number but different mass number are known as isotopes. For example, 3 isotopes of hydrogen, protium, deuterium and tritium. This is 1H1, deuterium is 1D2 or 1H2, tritium is 1T3 or 1H3. This 1 is the atomic number. Okay, we can say atomic number is same but mass number is different. Protium is 1, deuterium is 2 and tritium is 3. And this mass number is differ because of number of neutrons. We can say in this case protium number of neutron is 0. In deuterium number of neutron is 1. In tritium number of neutron is 2. Clear? Another example is chlorine having 2 isotopes. This is chlorine 35 and this is chlorine 37. Both have the same atomic number 70. Isobars. Atoms with same mass number but different atomic number are known as isobars. For example, carbon 14 and nitrogen 14, both having the same mass number. Okay, but their atomic numbers are different. These are isobars. Drawbacks of a Rutherford model. The Rutherford model cannot explain the stability of an atom if the motion of an electron is described on the basis of classical mechanics and electromagnetic theory. Now, what is this classical mechanics? Classical mechanics is a theoretical science based on the Newton's law of motion. It specifies the laws of motion of macroscopic objects. Clear? You can say the Rutherford model is compared with the solar system. And the motion of planets and sun can be described with the help of this Newton's law. Okay, if we apply this Newton's law to the electron, clear, then what happens? When a body is moving in an orbit, it undergoes acceleration. Clear? Speed is not changing, but direction is every time direction is changing. That's why it undergoes acceleration. And according to electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiation, or simply we can say when charged particles accelerated they should emit energy in the form of electromagnetic radiation. And when they emit the energy, then we can say the path of the electron becomes shrink continuously. Okay, this will shrink. Okay, and finally this electron should merge into the nucleus, and again we will get the Thomson model, miniature form of Thomson model. Okay, that's why we can say if we compare the Rutherford model according to this classical mechanics and electromagnetic theory of Maxwell, then atoms are unstable. Okay, actually planets are not charged, but electron is charged. That's why this classical mechanics cannot be applied to the electron. Another drawback is it says nothing about distribution of electrons around the nucleus and the energies of these electrons. Okay student, subscribe my channel to get the new video. Thank you.